we're going to try one more set of related rate problems, all based on this scenario right here. We have a rocket or a space shuttle launching into the air. And so as it climbs, there is a television camera stationed a good distance away that has to keep its lens focused on the rocket. Okay, so it's got to keep tilting and tilting to keep its lens on the shuttle. So there's a couple of quantities here that are going to be changing. First, the rocket will climb it steadily into the air, and I'm going to demonstrate this. I'm going to draw a triangle here and show you here how this is going to work out. Like, you could imagine that the horizontal of this triangle is how far the camera is stationed from the launching pad. Then as it climbs, the height, the vertical of this triangle will climb higher at the same time as the horizontal does not change. And then there's this diagonal distance here. So I'm now going to just kind of lock this in place, because this is going to be the primary shape we need to analyze in this problem. The situation is the rocket is going to launch and climb off the Earth 350 feet per second. The camera is stationed 1,900 feet from the launching pad, and we're going to solve a series of related rate questions at the instant that the rocket has been in the air for 12 seconds. A little warm-up exercise, which will actually help in a few minutes in the related rate problems, is just asking how high is the rocket 12 seconds after it launched. And that does not require calculus, since we know how fast the rocket is climbing, 350 feet per second. And we're studying this at the instant it's been in the air for 12 seconds. So a little bit of quick math here. If it's climbing 350 feet per second for 12 seconds, we're going to take the speed times the time and get the distance. And that's 4,200 feet. So we're going to be studying this rocket and some of the changing distances in this story at the instant that the rocket is 4,200 feet in the air, which is 12 seconds after liftoff. I think it's time we go look at what other things we're going to be solving, and then we're going to go back and label this picture a little bit better. The first related rate question is going to be to find the rate at which the distance from the camera to the shuttle is changing. Now, in this picture, that distance is the distance along the slant here, okay? Because the camera is 1,900 feet from where it launched, but as soon as the rocket's in the air, the shorter distance is going to be along this slope here. It's going to be the most direct distance, okay, from the rocket itself to the camera. On the next slide, we have a second related rate question. It's what is the angular rate at which the camera must continue to tilt back in order to keep its lens on the shuttle itself, in order to keep track of the shuttle as it goes up and up and up. Okay, in fact, I'm going to go ahead right now and copy that triangle over to that picture also. And we'll go ahead and we'll start working on this problem first here. I think the good idea now is to just label the quantities on this triangle. It seems like the edges of the triangle are going to be the important ones in part B here, at least. Now you could use whatever variables you'd like for these sides. Now I typically like to name them things that will remind me later what direction they're in. So for example, a vertical is in the same direction as the y-axis on a graph. So I might call this quantity y, and this horizontal quantity x, since it's in the direction of the x-axis. And let's just actually call this one z this time for the other side. which means maybe the answer to part A, we could also label this as Y now, since that's the label I'm using in my picture. So in B here, imagine the rocket climbing, climbing, climbing. And so the triangle, two of the three sides of the triangle are going to change. The Y value here is going to change. It's going to be representing the altitude of the rocket. And the diagonal will be changing also, but this one actually doesn't. But no matter how high the rocket is, this right triangle will be intact, and any right triangle, the sides are always related by the Pythagorean theorem. So let's actually write that equation as our starting point, that the hypotenuse z squared is equal to the square of the other two sides added together. And let's make a note of what we were given to start the problem. We're given that the rate at which the rocket climbs is 350 feet per second. So in this context, that's the change in y, or y prime. Other people might write dy dt, but we're told that is 350 feet per second. We were also told we're going to solve this instantaneously when the rocket's been in the air for 12 seconds. And kind of the warm-up exercise was to find out how tall the rocket actually was 12 seconds after launch, and that was 4,200 feet. Now, along the bottom of the triangle is representative of how far the camera is from the launching pad, and that is consistently 1,900 feet. It's a good time to make a note of, we actually know that one's rate, dx dt, or x prime. Now, we weren't told it, but we kind of were, in the fact that that distance is not changing. That distance is going to be remaining constant because the camera is not going to move from its location. So in other words, since it's not changing and that 1900 is constant, this derivative is going to be simply 0. Okay, now the other quantity that's going to come into play in a minute is quantity z. And since I'm now at this one instant of 12 seconds, and at that instant, the rocket's height is 4,200 feet, and the camera is 1,900 feet from the launching pad, I can actually use my equation, z squared equals x squared plus y squared, and solve for how far the rocket is from the camera at this instant, simply by taking those two quantities, 1,900 squared and 4,200 squared, putting them into my equation and solving for z. And I'm going to go ahead and have you guys put those into your calculator. So 1,900 squared plus 4,200 squared. I get a rather large number here. It's like 2,125,250,000. That's actually 21,250,000. So the square root of that represents the length z. For now, I'm not gonna simplify that further or type that into my calculator further. And then dz dt is actually what we're trying to find here. Okay, so it's time to measure the derivatives of this equation. So we're going to put a derivative with respect to t and apply it to all the terms. So each one of these quantities is a function of time, and so each derivative is going to use the chain rule, and it's the same technique every time. They're all just squared. So 2z times z prime equals 2x times x prime plus 2y times y prime. So now there's actually 6 missing quantities, but we've already accounted for 5 of them. At the instant that the rocket's been in the air for 12 seconds, we know that it is 4,200 feet high. We know the camera is 1,900 feet away from the base where the rocket launched from. And we know that the actual distance to the rocket is this quantity here, z. So we're going to fill all this in, and we'll be solving for z prime. In fact, what I'm going to do is I'm just going to do this. I'm going to just divide right now by 2z and put that here. And that'll make it, now I can just fill this in. So 2 times the 1,900 feet times x prime. But remember, we noted that x prime is 0 because the horizontal distance is not changing. It's constant. So its actual rate of change is 0. Then I've got 2 times y, which is 4,200 feet. And its rate is the rate at which the rocket's climbing, which is 350 feet per second. And we're going to divide that all by 2 times z, and z is that big square root I'm going to fill in here. And I encourage you now to solve or evaluate this with your calculator. Please note again, you don't even have to type this part in because it's all going to be 0. So it's really just going to be the upper right corner divided by this quantity here. I encourage you to pause the video just a second and do that calculation, and we'll check our answer together in just a minute. And I went ahead and entered this into my calculator also, and I got a numerical value of 318.888. And since this is the rate of change of z, whose label would be in feet, and it's the rate of change per second, then the rocket is moving away from the camera about 318.888 feet per second. Now what I'm going to do here is I'm going to copy a number of these values because we're going to use them again in the second solution. So when we go to the next slide, I'll have some of those copied over there. Okay, our last related rate in this problem about this rocket ship is we're going to actually study now how quickly this camera has to tilt to keep the rocket in view, which means we're actually going to be analyzing this angle theta right here that's formed between the ground and then the sight line to the rocket itself. But let's label this triangle again with the same variables as before. And so this time we want to we want to write an equation that involves the angle. And so hopefully you're thinking about maybe your trigonometric ratios. Now there are 3 trigonometric ratios that involve theta, at least the 3 primary ones: sine theta, cosine theta, and tangent theta. And if you wanted to involve the other ones, you could also write secant, cosecant, cotangent. Now what I like to do is write and use the one that involves the 2 quantities that are mentioned in the given information. Since we were told how fast the rocket is climbing, and we were told how far the rocket is from or launch pad is from the camera, that involves y and x. And so I'm going to use the trigonometric ratio that involves y and x. So it's time for me to think of those now as the opposite side to the angle and the adjacent side to the angle. And that was the tangent ratio. So I know that the tangent of theta, the definition is opposite over adjacent. But in this drawing, that would be the value y over the value x. And now it's also implied then that theta, the angle, is a function of time, because as this rocket climbs and climbs, every second passes, this angle is going to be growing. Okay, so the time passing along here is going to adjust the angle. So theta is also a function of time. And that's actually what we're trying to find. We're trying to find the rate of change of theta. So we would call that d theta dt, or we could just call it theta prime. Okay, theta is thought of as a function, which is the angle here, and we're going to assume the angle is measured in radians. Okay, so let's just write the equation again. Tangent of theta is equal to y over x. And we're now going to apply a derivative to both sides with respect to t. Okay, so I encourage you to make sure you recall the derivative of the tangent function. And the derivative of the tangent function was secant squared. So the derivative of tangent theta is going to be secant squared theta times the derivative of theta. And notice on the right side, I've got these two functions dividing, so we're going to actually write out the quotient rule on the right side. Okay, so you're thinking low d high minus high d low all over the square of what's below. So low d high is going to be x times the derivative of y, and then high d low is y times the derivative of x, and then square of what's below is x squared. Now, I'm solving for theta prime. I want to know what theta, the rate of change of theta is. I know all the values of the right side perfectly fine, but there's this secant of theta on this side that I don't have a value for. So it's time for me to rely on my trigonometry knowledge again. Secant is the reciprocal of cosine. But I know the cosine of an angle is the adjacent divided by the hypotenuse. And so if I think of this as the reciprocal of the cosine, and in this context, if the cosine would be x over z, the secant would be z over x. But I still want secant squared. So I'm going to make a note here then that secant squared theta would be z over x times z over x. That's going to be z squared over x squared. And I can now I can make that substitution in my derivative on the left side. Okay, so where I'm showing secant of theta, or secant squared of theta, remember that really means secant of theta all squared. And so that's how I got secant squared to be z squared over x squared, hypotenuse over adjacent. I'm actually going to put that in here now. Z squared over x squared, all times theta prime, equals x y prime minus y x prime all over x squared. And I'm actually going to attempt just to solve the equation right now for theta prime before I start putting all my numbers in. I happen to notice that I have x squared dividing on both sides already, so it would make a lot simpler if I just multiplied both sides by x squared. So now z squared theta prime is the entire left side, and then xy prime minus yx prime on the left. So notice if I just divide everything by z squared now, it's going to give me my theta prime. X y prime minus y times x prime all over z squared. So now it's time to just put the numbers in that I know. X, I know, is the distance from the camera to the base of the launching pad, which we were told was 1,900 feet. Y prime is the rate of y, which is the rate at which the rocket's climbing in the air, so that's 350 feet per second. Y is the instantaneous height of the rocket, 12 seconds after the launch, which we learned was 4,200 feet. x prime is the rate at which this distance is growing, which actually is 0. Z squared, I actually saw in some of my intermediate calculation over here, was basically from the Pythagorean theorem. Z squared was 1900 squared plus 4200 squared. So I'm ready to put all this in my expression now. So x is 1900 feet. Y prime is 350 feet per second. Y is 4,200. But then don't forget we're multiplying that times 0. So that really I don't have to look at anymore. And we're dividing it all, this time, by z squared. And up here I wrote that as 1,900 squared plus 4,200 squared. Now, to avoid complication on your calculator, I would encourage you to take this whole entire expression in the denominator and add it all together first, and then we'll do the dividing at the end. So we'll take the top part, 1900 times 350, and get 665,000. And then we know that this part is going to be that 21,250,000. So now we're just going to divide those. And I get this very small number here, 0.031. Now this is the one time where it's kind of difficult to understand the units from the calculation, because all the units in this calculation were in feet and feet per second. However, the context here is this is the rate of change of theta. In other words, d theta dt. And that implies then the unit should be the label of the angle, which is in radians, divided by the unit of the time, which is seconds. So this tells you how many radians per second the camera must tilt by. You notice that's quite slow. Even if you convert this into degrees per second, it's very slow because the distances are so big that, you know, the relative speed is quite slow for that angle there. Well, I hope this helps you guys, and we'll look to hear from you through email or Google Meet if you have further questions or want to talk over some of your homework problems. And have a great day.